The plan for today is to discuss thermalization, relative thermalization. And as you're gonna see, the structure of the lecture covers mostly classical aspects. The reason is that there are important things to clarify first at the classical level so that the aspects that are genuinely quantum, I can highlight them separately. And next week, we're going to consider examples that are the kind of many oscillators and caldera-Leggett. And there too, there's a classical version, quantum version. There's always a question of what are just aspects of exchanges of energy and thermalization that have to do only with exchanges of energy and changes in correlations, and what aspects really have to do with coherence and entanglement, okay? And one way of being concrete is classical mechanics provides a rigid, robust framework. You can think of it as a fundamental theory. You can think of it as a regime of full quantum mechanics. So I'm going to take point of view of, I do open classical systems. We discuss open classical systems, and then we do go to open quantum systems. And I'm going to try to state the generally unstated assumptions in this first part, then give you the simplest possible example about entropy in classical mechanics, and how, building on that example, we can discuss thermalization. These things are somewhat standard. There's a nice introduction that I like that is in this book on chaos and coarse graining that really clarifies the role of coarse graining. Is in Pulpiani and others, and also clarifies exactly in what sense Lyapunov exponents enter the analysis. I'm going to mention some aspects of classical mechanics that you find in this museum views of Ian Stewart, and the overall logic for the quantum theory, even though I'm describing the classical theory, is in this review of Marcos and others. Okay? Good. So I'm going to start with this. I'm going to describe the postulates. You recognize them. They have the same structure as the postulates of quantum mechanics. For classical mechanics, they generally quant-stated. We always assume that we know classical mechanics. We don't have to say what is a measurement. But as I'm going to use it, and I'm going to need to use them, I'm going to go through it step by step. And let me highlight it again. There is nothing, this is completely standard. It's just things that we generally don't say as postulates. So let me state the postulates. The first postulate regards states of a classical system. And the statement is that states are probability distributions in phase space. Okay? Not points, but probability distributions. Observables are functions in phase space. And the dynamics or the evolution, it's a linear partial differential equation given by the Liouville equation. Poisson brackets with the Hamiltonian. Okay? Let's conclude with the other two postulates as in quantum mechanics. Quantum mechanics, we generally describe the system as isolated and evolving unitarily. And then there's a Heisenberg cut. And then we connect that to predictions. They are useful, these Dirac-von-Neumann postulates, because they allow us to clarify the relation between mathematical structures and physical predictions, because it's not enough to do this. Then you have to say, when you make a measurement, what happens? And so here too, there's a Heisenberg cut. It is when you make a measurement, given a state and an observable, the probability of finding an outcome lambda of this observable is random and is distributed according to a probability distribution that is the marginal of the state restricted to this observable. Or if you want, you put a delta in here and you integrate. Okay? So there's a probability of finding some outcome. And if you measure that outcome, then now you know the outcome. So you have to do a Bayesian update. If you really want to give it a name, you can call it collapse of the probability distribution function, and the state after you have measured that observable is this one. Okay, so let me comment on these points, maybe, and then we go back. I just want to illustrate them with an example, because this is the example that I'm going to use throughout the lecture. And then we go back and I let you ask questions about the postulates, unless there's an immediate comment. So let me illustrate it with an example. Take a particle in a box, okay? Let's say it's a box of size L, and the box is rigid up to certain energy. I really want my phase space to have a finite symplectic volume. This is going to be useful. It's a free particle, so the Hamiltonian is the one of a free particle with these conditions. And now I have to say how I prepare my initial state of the particle. So the introductory mechanics that we learn is, you put a point in phase space, that is your initial state, and then you follow it, and this is the easiest problem in mechanics. Yeah, being a bit more careful in how you prepare something. There's going to be always some uncertainty in position and in momentum. Just to be completely concrete, imagine, like, we never think carefully about that for macroscopic objects because these ones are can be made sufficiently small. But let's say that this particle in a box is a rubidium atom in a trap, and the trap is sufficiently large that you don't need to think about quantum mechanics. The problem is really in the classical regime. And so there's an oven, rubidium vaporizes already at 200, 300 Kelvin, 600 Kelvin, 300 Celsius. Then they come out here. So at that temperature, they would come out Maxwell distributed with typical velocity about 100 meters per second, but you can collimate them. You can do a time of flight selector for momentum and also for position, enters the box, and then you close, you have it there inside, and you have prepared this state. Okay? So now the question is, how does the state evolve once you have prepared it? So time evolution. Okay, yeah, I have to check. Is it clear why the probability distribution evolves in this way? So first of all, the average position and momentum, this one, becomes this one. The average moves as familiar, but the probability distribution gets deformed. It gets deformed because me address it first mathematically. Mathematically, what you are solving is this equation. It's a linear partial differential equation, a fixed initial condition. So you just have to solve it. That's what I did there. And you start with this initial state. It evolves in this way. Now, is it that surprising? Well, if it was a particle localized here, I would have higher momentum, and so it moves faster. If it was down here, it moves slower. And you can think of this, and people often do that. They use it also for doing this kind of simulations. They say, well, this state is a mixture of many deltas. And so you evolve one at a time, and then you put them back together. But you can really think of that as just a trick for solving a partial differential equation. Okay? And once it reaches the wall, the particle reflects back. So the probability distribution evolves in this way. Now you see, it's getting tilted more and more. This tau naught, this is just the time of flight of the average position from side to side. And you can think of solving the differential equation for the state formally by just, this is linear, so you can just exponentiate it and find the formal solution, where this L is the Liouvillean. So this is really the analog in classical mechanics of what we learn in quantum mechanics as unitary evolution. Okay? Are there comments before I go ahead? There should be comments at this point. Yes.
The volume being conserved,
Mm-hmm.
is that because it's unitary?
Good. So the first thing I want to notice is that this changes shape, but the total symplectic area doesn't change. It's a probability distribution, the total symplectic area, or the integral. I'm taking it constant. The integral has to be 1 because it's a probability. So this evolution preserves probabilities, preserves positivity, and preserves normalization. Is positive trace preserving map. Where is C of CP of completely positive? There's no C. This is classical mechanics. Okay? So it's the classical analog of unitary evolution is symplectic transformation. Okay? It's going to be important in a moment that this is just two-dimensional phase space, is 1 degree of freedom, so there is not much that can change, but as soon as you have many degrees of freedom, this kind of evolution preserves more than just the symplectic area or the symplectic volume. Okay? The same way as a unitary transformation preserves more than just the no. Okay, more comments.
So you're going to talk about chaos and thermalization and stuff. So
yeah,
maybe this is too early, but
go ahead.
Having that finite delta Q and P, is that going to be necessary to see all the notions of chaos or get it to whatever?
Yeah. And I think this is an important point. So let me say something that is often presented at the introductory level in this way. Chaos is take 2 points in phase space and then you follow them and they diverge exponentially, as if you could measure the distance between 2 points in phase space. But in phase space, there is no notion of distance. What's the distance? In what units would you even measure it? But in phase space, there's a notion of symplectic area. So you can follow these symplectic areas and ask how they change. In 2 dimensions, they're conserved, so you cannot have any chaos. But as soon as you go to higher dimension, many particles, then you can start asking various symplectic areas in various directions for various subsystems, and you find that some are increasing and some are decreasing. In total, the volume has to be preserved, so there are as many stretching as many contracting, but there are some subsystems for which the marginal probability distribution spreads exponentially with the Lyapunov exponents. And if one goes check how Lyapunov exponents are actually computed numerically and even defined mathematically, they're never done with 2 points in phase space. You always take a box and you look at how the box deforms, or you take a probability distribution and you look at how the probability distribution changes. Or even better, you look at the entropy. And you look at how the entropy increases linearly in time. This is the Kolmogorov-Sinai rate. And the relation to the Lyapunov exponents is Pessin's theorem, Pessin-ECI mathematics. Okay. So one more comment before we go ahead? No, let's go ahead. I have comments. I think we already caught one of the comments. Chaos. So the first remark is don't confuse states with observables. Q and P are not states, they are observables. You can think of a state as the Dirac delta. This is a probability distribution. I'm considering finite precision of preparation that introduces a finite dispersion. Note that you can get back the delta, this Dirac delta, when you set dispersions to 0, but be careful. This limit is pathological in classical mechanics, because if you send these ones to 0 first, there is no way it can spread. You can wait as long as you want. They're never going to spread. And so what is as long as you want? For the particle in a box is this time of flight from wall to wall. Now, if I go here and I prepare a delta here, that is going to remain a delta. This is going to evolve here, 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 here. It's never going to spread. But if I give it an arbitrarily small uncertainty, with time that uncertainty is going to stretch in one direction and contract in the other. Okay? There's a fair question of why don't we see this in everyday life all the time? This is an isolated classical system. Most classical systems we interact with, they have some dissipation. And so all the questions, or at least many of the questions that we ask about quantum theory, that is, what happens when the system is open, why some systems thermalize and some others don't thermalize, many of those questions are already present here. Quantum mechanics, there is just more physics, but also all of that is all there. Okay, so for the simple example that I have just this time scale. For a chaotic system, I have Lyapunov exponents, and this pure state limit, it's a limit. There are states in the theory, but I have to be careful. It's better to take them finite and arbitrarily small, but then allow T to be arbitrarily large. In quantum mechanics, the pure state limit is under control. Second remark, the algebra is commutative. In quantum mechanics, it's not. There's a typical scale, it's h bar. Evolution, I was already saying this. It's a linear PDE. It preserves positivity and normalization. It does more. It deforms the probability distribution in such a way that its entropy is not changing. A bit like in quantum mechanics, unitary transformations don't change the entropy. So unitary, symplectic, related in this way. All the things before were differences. This is really like similar behavior. Comments? Yes.
Sorry, could you explain again why pure state limit is pathological in quantum mechanics?
Yeah, so the argument that I was giving is, let's call this one a pure state. It's the limit where I send the dispersions to zero. Once I have that to zero, then I can evolve it as much as I want. It's never going to spread, because the spreading is, you start with initial spread and then it can be enhanced. But if you start with zero, you can never you can multiply it by any number. And so there are two limits, T to infinity and dispersions to zero, and these two limits don't commute. If you first take the pure state limit, you're never going to see chaos.
Yeah.
While if you fix this arbitrarily small, then you have all the rich structure of classical mechanics. I have to admit that I'm using the standard notion of distributions that we are familiar with. That doesn't mean one cannot come with better mathematics where a delta filaments and gives some model distribution. As far as I know, that mathematics is not developed. No, mathematics sends a point in phase space into some filaments. But as physicists, we always have our trick of, keep things finite and then take limits. Okay? Yeah. So you have never seen this. There's a set of techniques in mathematics that really help, that are from symplectic geometry. And this aspect that I was telling you about, this has a name. It's a Gromov no-squeezing theorem, also known as the symplectic hammer. And the reference I was giving you is a Newton view of Jan Stewart. If you are familiar with the symplectic geometry, use it. If you're not familiar and you are curious, this is a nice article to read. It does make the point that there is a notion, there's a rigidity. Right? If you have some probability distribution and you say only the volume is fixed, then you could take the eye of a needle and make the distribution squeeze as much as you want and pass through the eye of a needle. But symplectic transformations are more rigid than that. They don't preserve just the symplectic volume. There's a list of quantities that are preserved. If you want, they're called symplectic capacities. If you want, they are areas in phase spaces planes. They are really the classical analog of Heisenberg uncertainty relations. If you start with delta Q, delta P, that is non-zero, this product at the beginning, then you can change one and the other, but this product cannot go below that. And these developments in mathematics, they are not that old. Arnold introduced it as a problem in '85, and since then this has exploded as a field. Okay? I'm going to use a little bit of those techniques because they really help. It's the same as when you learn quantum mechanics. You learn a little bit of functional analysis, Hilbert spaces. Classical mechanics, that's useful. If you have done some general relativity, it's not differential geometry with Lorentzian metrics, it's differential geometry with symplectic structures. Okay, comments? Yeah.
This is a very basic question, but is a symplectic transformation the same as a canonical transformation?
Yes, they are synonymous. Exactly the same.
Like the whole morphism?
Yes. Yeah. Good. Two more comments before going ahead. I should comment on this thing of measurements. Let me give an example. Suppose that I measure the energy. The probability of finding a certain outcome is given by the marginal distribution. You see the formula is very similar to the one in quantum mechanics. Probability of finding some energy given a density matrix. There's where is the difference? In classical mechanics, all probabilities are marginals of some state of the universe that is a PDF. In quantum mechanics, you have a state of the universe that is a state in Hilbert space, and there is no PDF of the universe. The obstruction is that you get marginals out of the state in the Hilbert space that don't necessarily satisfy the inequalities for marginals. This is called Bert's theorem. Now, yeah, one more step. After a measurement, post-measurement state, or if you want preparation of a state, let's say I start with a free particle and I find outcome E. After of the energy, the state after is selected to be E, so it can be this way or this way, but same energy. And you can compare this to a non-selective measurement in quantum mechanics, one of the POVMs that we saw. And the POVMs that we saw, they are of this form. And in general, if you do a non-selective measurement, that is, you sum over all possible outcomes with the probability of the outcome, you get this map, the CPT map, that is not the same as the initial state. And the reason is that you lost coherences. There's nothing like that in classical mechanics. Coherences are not there. If you integrate this back, you get back the original state. Okay? Good. So that's all I wanted to cover for classical mechanics, the postulates. Now I'm going to use this. So have you ever seen this in this form? Comments? I generally think of classical mechanics in this way. That's the version that I assume classical. Let's go ahead.
I have a question.
Yes.
How does this reconcile with, I guess, the version of classical mechanics that we learned, where you do have points in phase space that are, I guess, the pure states that you're saying?
Yeah, instead of thinking of them as pure states, a consistent way is saying you always speak about averages and never about the variance. Average position and momentum evolve according to the classical version of RFS theorem. Yeah, there's a huge literature on this kind of things. In statistical mechanics, you really often use them without declaring structures. No? Von Neumann's wrote a lot about this. sometimes called the von Neumann formulation of classical mechanics. So now that I have this, now I can speak about entropy. Because now I have states, I'm taking them seriously. I'm not committing to an interpretation of classical mechanics. I don't have to say where those probabilities come from, if it's my ignorance, the ignorance of the person preparing the state. I have states, now I can speak about probabilities in the same way as we did when we were doing hypothesis testing and all that before. So, if the puzzle is what is the entropy of a particle in a box, now I can answer by saying, well, first of all, we learn, when we speak about entropy, let's declare entropy in the sense of relative entropy with respect to what reference state. So I'm going to choose my reference state, my hypothesis, as the one where I don't know anything about the system, apart from the fact that I actually prepared the particle in a box. I did this procedure with the oven, the collimator, the time of flight. I checked, it's inside, but it's inside means it cannot have energy so big that it breaks the box, and it's inside the box. So this uniform distribution is the one that I'm going to take as reference state. Okay? And by construction, it's stationary. Now you can check the Liouvillean on this one is 0. So now I can ask what's the relative entropy? Relative entropy of some state with respect to that reference state. The reference state was just that constant is here. This quantity by construction is 0 or larger than 0. The common practice is to call entropy of a probability distribution this relative entropy with respect to the relevant state. So standard notion of entropy up to a constant, is this constant. I'm going to adopt that practice so that the entropy grows instead of decreasing. This minus sign is just that. Okay? Comments? You see where I'm going. I want to get a plot of the entropy as a function of time. I need models for that so that I can actually do it. Next week, we're going to do harmonic bath. The week after, random matrices and spin systems. Goal here is the simplest possible system, just one particle in a box. Can I plot the entropy as a function of time? What does it look like? Independently of thermalization, just one particle, so it's not going to thermalize. So now I have a notion. Entropy as function of time. The comments.
What kind of box? A square box?
I took, it's one dimensional, so it's an interval. So if you want, I was saying rubidium atoms, they enter this optical trap.
Yeah, I'm just saying you're saying you want to have a plot of this entropy as a function of time. Is it going to be a one-dimensional box?
It's going to be a one. I need exactly this example.
Okay.
Yeah. Do you already have a guess for what is going to look?
It's not going to. My guess is not going to change.
Yeah, if the evolution is Liouvillean, the entropy should remain independent of time. So this quantity that I wrote here depends on t, but actually shouldn't depend on t. I agree. Right?
Yeah, I'm just wondering if you make the walls of the box messed up in 2D, let's say, will you be able to see something?
So let me emphasize it because this is really the point that I want to draw. It can be arbitrarily many particles. Box can be arbitrarily complicated. You can put arbitrary interactions between the molecules. Van der Waals are more complicated. This entropy is not going to change in time because this is an isolated classical system. So when we speak about thermalization, we're not speaking about this one. We're speaking about some subsystem, or if you want, another way of saying it is some coarse graining. Coarse graining is a word for subsystem here. Let me go ahead. I made the statement, but I didn't prove it. This is the only page where I prove that statement. You find it in the literature in many ways. You can go check it. I want to show you how you do it, how transparent the derivation is. Once one knows that minimum of mathematics, just a little bit of symplectic geometry. So it's like a way of inviting you to go look at symplectic geometry, because it's like when you want to learn quantum mechanics, you go check what is a Hilbert space. No, unless one is doing 2 by 2 matrices, and then one goes check what is linear algebra. So the statement or the theorem is the entropy of an isolated classical system does not change in time. If this was a quantum statement, it would be the entropy of an isolated quantum system doesn't change in time because evolution is unitary, and unitaries, we know how they work, and it's one line. I'm showing you the analog one line for a classical system. So all this is preparation. So what does it mean evolve in time? Well, this is our Liouville equation, how a state evolves in time. Okay, and you see how I'm writing it. You can write it as P dot equal H with P. It's good to give a name to this thing. This is given some observable in phase space, you can check what flow in phase space it generates, what vector field it gives you. And it's this differential operator. Okay? Now, it's annoying to work with Q and P, it's like working in coordinates. It's much better to put things together and work covariantly. So one gives a name psi to points in phase space. And the Poisson brackets, they become a symplectic structure when you write it that way. If you do Q with P, it's +1. If you do P with Q, it's -1. Otherwise, it's 0. And the measure, when you integrate, that is a symplectic measure. Okay? There's another thing that is useful, that is Stokes' theorem in phase space. If you take the derivative of a function and integrate it, you get 0 up to boundary terms. So we assume that they are not there. Okay? It's like a divergence theorem. So now let's check a conservation or normalization. If this is 1 at the beginning, normalization, the time derivative should better be 0. Time derivative, I bring it inside, and this is a derivative along the vector field H. I use the theorem, 0, done. Okay? This is what often you find in Wikipedia, Liouville theorem, they call this one Liouville theorem. And it's a longer page where you check the pieces cancel, but this is the geometric version. Now I need a one for entropy. I want to show that entropy is conserved, assuming that the reference state is stationary. How do you do it? Same thing, you just have to do a bit more steps. The derivative, you derive with respect to time this piece, you get 2 terms. One is the same as before, so it's 0. The second, it's a Liouvillean. This Liouvillean, you can write it as a total derivative. You can integrate by parts if you want. This is a total derivative, so it's 0. This one is the same as before, so it's 0, and we're done. I don't know if it was too fast, it was too slow, but I'm really showing you that you could do all these calculations with more elementary methods. They just hide all these structures. It's in the same sense as if you know what is a unitary transformation, there are things that you don't prove by plugging in matrices and checking that there are cancellations. Okay, comments before I go ahead? Yeah.
You said that the entropy doesn't change for assuming the stationary reference state. So if that isn't true, then we have a different change in entropy, even if it's in a closed system.
Yeah, so if I have a reference state that changes and I evolve both the reference state and the state I'm interested in, then then it doesn't change anyway. No? But what I'm calling entropy has only one label and not the other, so that's why I'm big. Okay? This is important if you're doing things like you're moving a wall as a piston, because that changes the reference state. One has to take that into account when one looks at yeah. Yes. Okay, so there's a puzzle that we know the answer to now. Where does all change in entropy come from if the total entropy cannot change because it's constant? I'm not saying it's 0, Quantum mechanics, you could say you start with 0, the state is pure, and then it remains 0. Yeah, I'm not starting with 0, I'm starting with some finite value, but it cannot change that value. So where does all the entropy change come from? I'm going to identify 3 sources. The first is, if you start with your system and you restrict to a subsystem, that is going to increase the entropy. This restriction is computing the marginal distribution. This restriction is ignoring additional data. This restriction is the restriction for that makes states less distinguishable because you have less information about them. And so you can use this monotonicity of relative entropy under restriction that, written in terms of our notion of entropy, it's an increase in entropy. Okay? There's a second mechanism that changes the entropy by not increasing it, but decreasing it. If you make a measurement and you learn the outcome of the measurement, you ask what's the state after you have learned the outcome of the measurement, then you know more about the state, and the entropy decreases just by Bayesian update. Okay? So these two are quite immediate. These are statements that you say what you're doing, and then you know exactly what is happening, either increases or decreases.
But what's this comment about uncorrelated reference?
Reference is this reference state with respect to which I'm doing the calculation. I do need that to prove this one. If I don't assume it, this is not really the entropy. I have to add more caveats.
So if it's the uniform distribution in the box and you
if you have 2 boxes and you take uniform distribution over the 2 boxes.
Okay. Yeah.
Yeah, you see, this is the kind of unstated assumptions that are always there, but we never speak about them because we just speak about entropy, not relative entropy. But you're assuming that when you make this statement.
Mm-hmm.
Okay, so here's the last one. This is the tricky one, the one for which you don't have a theorem. You look for regimes. Take some initial state, restrict it to a subsystem. Then you have an initial entropy. Now, this initial entropy can either increase or decrease. Why? Well, because there was a theorem for the Liouvillean, but once you integrate out degrees of freedom, the evolution is not Liouvillean anymore. The same as unitary you trace, what is left is still a positive normalization preserving map, but you're interested in how it changes not from the initial value to any value, no? But does it go up and down, or does it strictly increase? And so here is where notions like, does the system have a memory? Is there a Markovian regime? Can we write Lindbladian for this classical system? All of these arise. And so what I'm going to do is consider concrete models and show how tricky this is and why in some cases some things arise and why in some cases we don't have to worry about that. Yes.
What's your A and B here?
Yes. So did I have the... Okay, so think of, let's say, many particles, NA particles in a box and B particles in a box. If you take them all together, you can always restrict to one of the 2 boxes. So A and B just means there's a large system and there's a subsystem A and a subsystem B. I'm being completely general. I only need them to be subsystems. But one example is here.
Hamiltonian can not have to be the Hamiltonian of the whole system.
Yeah, so here it's the point, no? Suppose that suppose if here there's an interaction BAB, then this is different from 0. If there's no interaction, then clearly it separates in evolution of A and evolution of B. That's what I mean. Okay. Okay, so I'm ready for the example. I'm gonna work out the example for the particle because I think it shows something that, well, it's solvable, so it's worth seeing explicitly what happens. So what I'm gonna consider as a subsystem is just one particle in one dimension. Well, subsystem is what you have access to, what you measure. If it's two particles, you say you measure one of the two particles. So maybe you measure the average position of the two and the average momentum of the two. If you have one particle, you can still measure, for instance, just the position. You have something that takes a snapshot, flash, and you know the position, but you don't know the momentum. You record it for this state, you get this probability distribution. The particle is within this range. Okay? So if you want, it's the marginal with respect to Q. Okay? And now this is a probability distribution that evolves in time, but its evolution is not million. We know to compute it, you just evolve the full probability distribution, the state, and then you marginalize. So at initial time is this localized thing, but then as time goes on, if you are at, let's say, 1/3 of average flight time, it opens up and you wait a bit longer. Now, the probability distribution is bouncing off the wall. And so you start seeing this kind of effects. It's more likely to find the particle here. And if you wait long enough, let's say 10 flight times, this probability distribution essentially becomes close to uniform. The state is not the uniform state. The uniform state would be a uniform distribution here and here, microcanonical state. So clearly the state is distinguishable from a thermalized state or a microcanonical state. But if you look only at a subsystem, you cannot tell. The relative entropy between the state of the full system and the thermal state can be extremely large. But as soon as you restrict to a subsystem, to some observables, that relative entropy can go to zero. And this is what one means by thermalization. Thermalization means there's a set of observables that cannot, after some time, cannot tell anymore a difference between a thermal state and the actual state of the system. Okay? I didn't have to coarse grain in any sense different from saying I'm looking for a subsystem. Yes.
If I look at the whole thing,
Yes.
the subspace, and I wait long enough,
Yes.
will it come back to the original state?
Yeah, I see your question. Yeah, it can. It definitely can.
So what will it look like over here in the subspace?
Yeah, let me think. I take it back. There's something that happens here. So if this was an oscillator, it wouldn't. If it's an upside down oscillator, you can compute the Lyapunov exponents. So if it's an upside down oscillator, this keeps spreading. It's never going to come back. Now, this is just the boundary case between the two. This is a logarithmic instability because it's a flat direction. And so suppose that there were no walls. This one up here will keep spreading, and that's it. Yeah. So it is a sort of special case. Yeah, there's not a recurrence time in this one. But if you take a system of n oscillators, then you should expect a recurrence time.
And also for the subsystem.
Yeah, so now let's look at the subsystem. So these were just probability distributions for the position. But once I have the probability distribution, then I can ask what's the entropy of the subsystem. So this is the exercise that I worked out. This is the entropy as a function of time. Okay? So I start with my probability distribution localized somewhere, some momentum and some position. How localized? Well, you see it's -2 divided by 0.69 is about 3 bits away from the uniform distribution. And then the entropy starts increasing, as we always expect, till it reaches some maximum. Does it increase in a monotonic way? Well, no, there is no mechanism that makes it monotonic. What is this first DP, this memory? Well, if there was no wall, this would keep spreading and the entropy would keep increasing. But because of the wall, you have things that come back, they have a memory of what went that way, and you're seeing it in the entropy, seeing it here. 1 travel time, 2 travel times, and every time it's a smaller contribution. And this is a super simple system. If you work this out for systems where there are many more typical time scales, these fluctuations are way smaller. But when you go to long times, you can still estimate how big they are, the fluctuations near the average distribution. Okay, the statistical fluctuations of the entropy. So when we look at the CPTP map, there are statements that we make that is in quantum mechanics, fix the initial state factorize and then choose any other state, any other time, then it's larger when it's with respect to the initial one. If you say that it also has more properties, like it's for any couple of times, then you're assuming more, okay? And as soon as you assume, I get to the point where I assume that there's a Lindbladian, then this curve becomes monotonic, and we're going to see it as an approximation next week. The approximation where for a many-body system, this one is monotonic. But if you don't do that approximation, you track the system and define it, I should say, the closest system corrections, you're going to see these memory effects. Okay, comments on this?
So to get this thermalization, you need both coarse graining in the sense of restricting your set of observables and an initial spread in the position of momentum, or would it have been enough to start with a point and then the partial trace?
Good, good. So if you started with a delta, the delta would never spread. And so you would never get thermalization. You have to assume that you start with some probability distribution and then you evolve that probability distribution.
So the marginalizing doesn't help.
Marginalizing doesn't help. Because if you take a delta and integrate out some variables, you still get deltas.
Yeah, I was just thinking over some bigger set or something, but maybe not. Okay.
Yeah, but as soon as you take some narrow, well, like, let's not take a delta, let's put some epsilon that makes the dispersions finite.
Yeah.
And then you evolve it, then you're going to find that in general, there's going to be some directions that are stretched, some directions that are squeezed, a bit like you can see for a chaotic system, you see these pictures of this filamentation, they are of that kind. They are supposed to represent this kind of phenomena. And now you look at a subsystem, and you can always find a subsystem where the entropy doesn't change, where the entropy decreases. You just have to find not just the Lyapunov exponents, but the Lyapunov axis. And you can align with the Lyapunov axis where things are contracting, or with the Lyapunov axis things are spreading. Typically, a subsystem is defined not as adjusted to the Lyapunov matrix. You define first, you say, well, I have access to these observables. Maybe they are just local observables, and the Hamiltonian has interactions between the local parts. So when you do that, then you are not adapting your subsystem to the dynamics. And what is going to dominate the increase in entropy is just the positive Lyapunov exponents, and the negative are not going to. Good. So These last 5 minutes are more qualitative. They are supposed to bring together ideas and then they are concrete in the examples that I'm going to discuss next week. So this is more general structure. I'm going to summarize. So take an isolated classical system with some interaction between part A and part B. Start with some initial state, probability distribution. Wow, let's assume that it's peaked somewhere in energy and not completely spread in energy. It's gonna be clear later why. If you take something that is localized in the space, it's also localized in energy. Take a reference state, something that you're never gonna touch, something that is uniform and with an upper bound on energy that is sufficiently high, so that you can then forget this one. Do the Liouville evolution. The entropy of the isolated system doesn't change in time, but generically, a subsystem is going to have an entropy that changes in time. Okay? In what way is going to change? Well, thermalization is the phenomenon where you start from the initial entropy and you're going to end up with fluctuations around the thermal entropy. This initial phase in a classical system has just to equilibrate the energy and the correlations. In the quantum system has to do more, has to take away also the coherences. And the time scales for equilibration and the coherence, they are not the same. One of the two can be much faster than the other. Then there are these fluctuations. The size of these fluctuations also depend on the initial state and on the dynamics.
This reference state probably doesn't factorize into A and B, right? Because of the interaction.
Because of the interaction. So there is where one has to decide one is interested. The reference state, once one has learned what happens, one then can update the reference state. No, it's like now I learned more about the system, I can ask more refined questions. And so one standard way of doing it, that is the one where one just speaks about the entropy, is you just assume that it's factorized. This one is not factorized. So if you take this one and you split it, people do canonical typicality. They don't take for the subsystem the Gibbs state. What they take is something that they still write as a Gibbs state, but with the Hamiltonian of mean force. It is essentially taking this, integrating away, and getting still something, and then you are calling that the reference state for the subsystem. Okay. Here's the final remark for this part. Within a thermalization time, you go to a state where the system is still distinguishable from the microcanonical state, but when you restrict it to a subsystem, it becomes indistinguishable in the sense that the relative entropy goes to 0. And all this is classical. What quantum mechanics adds on top of that is that you can even start with an initial state that is pure. And for a subsystem, you get thermalization. In that case, all of the entropy, you can argue, is all due to entanglement, because there was no uncertainty in the state. The state was pure and unique and given. So for the Caldera-Leggett model that we're going to discuss next week, you have a structure that is of this kind, let's say many oscillators, and an interaction between the two. If you start with an initial state without correlations between A and B, time evolution is going to introduce correlations. And then you can ask, if you wait a long time, if the restriction to A is distinguishable from the thermal state. And the statement of thermalization is that this relative entropy goes to 0. And so in the same logic of hypothesis testing here, this is not going to be 0. The point is how small it is. If it's really small, you need to make really many measurements to tell this apart. And I'm gonna find it's exponentially small in the size of the system, but physically means they are practically indistinguishable. Do I have one comment? We are gonna discuss these things next week. Once you're there, then you can discuss temperature. No? How do you get temperature? Well, if it's indistinguishable from a state with fixed energy, then temperature is just how the entropy changes with the energy. And you can prove under some assumptions that the microcanonical state restricted to the subsystem is the Gibbs state. And all these things can be said in complete generality, but with lots of caveats about what are the assumptions for that to happen. So I think it's way better to take one example and work it out in detail so that we can track where we're making the approximations. Okay? Okay, comments?
Are you gonna discuss maximizing entropy at some points? Like, okay. Okay.
As a way of updating your reference state.
You mentioned I guess the point of that you made that you only get a change in entropy when you restrict to subsystems, right? So subsystems is like the main thing when you think of change in entropy.
Yeah.
But I
The
guess
system has to be open if you want.
But
Yeah,
then I guess
change.
there will be some subsystems for which there is no change in entropy. Is that right?
Yeah.
And is there any characterization of those subsystems?
Yeah. So there is a thing that it's really leader.
Is it related with the interaction
Yeah,
or
it's
is
related with the interaction, and there's this thing notion of decoherence-free subsystems. It is really, once you look at the interaction, then you can identify the subsystem that is non-interacting with respect to that interaction.
looking through the observables? So
Yeah, you can, yeah. So there are always, you can always find the coherence-free subsystems, unless the interaction is maximally chaotic. If it's a random matrix, you're not gonna find that the coherence-free subsystem. But as soon as the interaction is generated by a finite set of observables, you can look for what commutes with those observables, and that remains free. And so often presented as decoherence-free, but that is true already at the classical level. And in a sense, this is important because we don't see that everything opens up and thermalizes. There are lots of things that don't thermalize, and there's a good reason for them not thermalizing. They're really decoupled. It's collective degrees of freedom, like the average the center of mass position of an heavy object. That's essentially decoupled from from the thermal fluctuations.
and I guess that depends on the particular system, like that
Yes.
set of observables.
Yes.
It's not like a general result on that.
Yeah, one can prove a theorem given an Hamiltonian with a certain set of interactions. What's the decoherence-free subsystem? Yeah, it's more useful to have something concrete. Really. Okay, that's all for today. Thank you.